Hello everyone, I'm Ilio from Nanyang Technological University, and I'm going to present our work about RESTful API testing, which is entitled MOREST Model-Based RESTful API Testing with Execution Feedback. This work has collaborated with our industry partner Huawei. So cloud computing plays an important role in current cloud platforms. According to the market report, cloud services have rapid growth. Besides, there are over 14.4 million users access cloud services. Finally, the whole market reached over 300 billion with more than 15% yearly growth. Therefore, the robustness of cloud computing service is critical. Bugs may lead to cyber attacks, which cause financial losses. So first of all, let me introduce what is a RESTful API. REST stands for Representational State Transfer. A RESTful API meets the constraint of REST style. For example, we can use CRUD operations to design RESTful APIs, which is known as create, read, update, and delete operations. So currently, RESTful APIs are widely used in cloud services. OpenAPI specifications are used to describe RESTful APIs in a formal manner. So OpenAPI specifications contain two parts: the API endpoints and the information of the object's schemas. The specification also defines CRUD operations, input parameters, responses, and so on. There are multiple testing techniques have been applied into RESTful testing. One of them is grammar-based fuzzing, like pitch. However, when developers conduct grammar-based fuzzing, a lot of domain knowledge is required to formulate grammars. And for each new service, developers need to implement new grammars. Another technique is white box RESTful service testing. It requires to access source code of system under test, which may not easy to do when third-party testing. Besides, the heavy overhead for code coverage collection is another trade-off. As a result, a lot of RESTful testing techniques are focused on black box fashion, like RESTler. Black box techniques are known as lightweight and scalable techniques. Let's talk about some typical examples of black box RESTful service testing. One of them is bottom-up generation, which RESTler does. It starts with single APIs and updates calling sequences incrementally. One drawback of RESTler is that the search space of calling sequences is huge. Another way to generate calling sequences is by a top-down way. At first, it builds operation dependency graph, and then it traverses the ODG to generate test cases. One limitation of this way is that it is heavily relying on the quality of the operation dependency graph. In this project, we have proposed an adaptive generation way. We combine both top-down and bottom-up styles to generate calling sequences. It is scalable and efficient. One of the challenges in RESTful API testing is how to infer API calling sequences from the Open API specification. For example, how can we get these coding sequences from its specification, like shown in the slides? So before going to our solution, let's see how the other work has been done together. So first of all, let's say operation dependency graph, which is known as ODG. So ODG models data dependency among operations, which can be inferred from the Open API specifications. The ODG is a graph G where V is a set of nodes and E is a set of directed edges. For each node V in bigger V corresponds to an unique operation in the Open API specification. The graph is said to contain a directed edge E, where E equals V2 and V1 for V1 and V2 in bigger V, and V1 equals to VE if and only if there exists a common field in the response of V1 and in the request parameter of V2. Two fields are common when they have the same name if they are of atomic type, for example, string or Boolean, or when they are related to some schema if they are not in the same type. So following this definition, V2 from V1 means that V2 depends on V1. So a property graph is a directed edge-labeled attribute multigraph, which consists with V, E, lambda, mu, where V is a set of nodes, E is a set of directed edges, lambda is a function from an edge labeling assigns a label from the alphabet to each edge, and mu is a function assigned key value pair of property to the edge of node. A RPG is a mixed edge label attribute multigraph with where V schema is a set of schema nodes, V operation is a set of operation nodes, EOS is a set of directed edges pointing from a node in V operation to a node in V schema. ESO is a set of directed edges, each of pointing from a node in V schema to a node in V operation. ESS is a set of undirected edges combine two nodes in V schema. EOO is a set of undirected edges combine two nodes in V operation. Lambda SO is a set of labeling functions to label edges in ESO. Lambda SS is a set of labeling functions to label edges in ESS. Mu schema is a set of functions to assign properties to nodes in V schema. And mu operation is a set of functions to assign properties to nodes in V operation. Note that RPG is not exactly a property graph because it is a mixed graph, while the latter is a directed graph, and this is the only difference. This figure shows the detailed workflow of MOREST. To test a RESTful service, MOREST first takes its Open API specification as input to build the RPG. After building the initial RPG, MOREST uses it to generate call sequences and replace the API calls in the call sequences with actual requests. Then, the generated test cases are fed into the target RESTful services, and MOREST shall collect the responses. By analyzing the collected responses, MOREST reports the detected failures for bug analysis. Moreover, MOREST also uses the response to refine the RPG by adding missing edges and removing invisible edges. The refined RPG is then used for generating MOREST test sequences. This marks the end of one iteration, and MOREST will keep testing the target RESTful service and refining the RPG until the time budget is reached. With the Open API specification, MOREST can build the initial RPG consisted of nodes and edges together with their properties or labels, which may contain false edges or miss some edges, and MOREST will refine it with dynamically collect feedback later on. Here, we compare the RPG model with ODG. The first difference is that ODG contains only the operation nodes and their producer and consumer dependencies as edges, while RPG has more types of nodes and edges. The second difference is that RPG allows nodes and edges to have properties and labels. Here we introduce how MOREST uses RPG to generate test cases. In general, this requires two steps. First, MOREST traverses the RPG and aggregate visited operations to form coding sequences. Second, MOREST generate concrete inputs for the API in the sequence to build test cases. In general, the idea of this algorithm is to visit every schema in the RPG and collect the operations related to the schema to build up coding sequences. While accessing a schema, we can recursively traverse other schemas which are connected to current one, collect the related operations to build new call sequences, and combine the new call sequences and the existing call sequences to building longer sequences. The generated call sequences cannot be directed for testing since they are just sequences of operations without concrete parameter values. For a given operation, if its input parameters are not from the response of other operations on the same test cases, they are decided as follows. If the operation has been called correctly before, MOREST assigns a high chance of using the parameters of the last successful run. Else, if the Open API specification have specified the valid range of values for the operation, MOREST has a high chance of selecting values from the valid range. Otherwise, MOREST will just use random values. The initial RPG generated by Open API specification may contain errors. New edges are added to an RPG in these scenarios. First, the most straightforward case is where the response value from an API aligns with a certain schema, but it is not documented in the specification. Second, the ages of ESS are added after the collection of execution feedback. Finally, the last scenario is where the ages belonging to ESO and EOS are added based on the inferences used for building ESS. As for age deletion, as an operation, if its input are from other operations on the same code sequences, and it fails to execute correctly after several tries, then the age pointing from the respective schema to this operation is temporarily recognized as infeasible. We have implemented MOREST based on Python. We are going to answer the following research questions with evaluation. First, how is the code coverage and operation exploration capability of MOREST? Second, how is the bug detection capability of MOREST? Finally, how do RPG guide and dynamic RPG updating affect the performance of MOREST separately? So evaluation data says we build the evaluation benchmark with 6 open source RESTful services shown here. In the benchmark, 4 services were selected from the UMaster benchmark. Additionally, PetStore and Bitbucket were also included. We use 3 state-of-art black box RESTful testing techniques as baseline to study the performance of MOREST. The UMaster black box mode and REST test string and RESTler and MOREST no RPG and MOREST RPG only. So in the first research question, we can find that MOREST achieves better code coverage and robustness in most cases. For the bug detection capability, we can say that MOREST achieves the best performance in bug detection. So finally, RPG and dynamic updating enhance the bug detection and coverage of testing generation. So finally, we propose MOREST, a model-based black box RESTful API testing technique. And MOREST learns from the Open API specification to build a RESTful service property graph, which is known as RPG. And MOREST can use RPG to provide high-level guidance for code sequences generation and refine the RPG with execution feedback. Thanks for your listening. If you have any questions, please ask. Okay, thank you.